Bismillah. Welcome to Think Math. In this lesson, we will solve absolute value equations and inequalities, both graphically and algebraically. For every worked example, we will first see the solution on a graph and then confirm the same answer step by step using algebra. By the end of this lesson, you should be able to solve absolute value equations graphically and algebraically, solve absolute value inequalities as shaded regions in the plane, and check that every answer agrees with the distance meaning of absolute value. Let us begin with the main idea. Absolute value means distance. The expression absolute value of x minus 3 represents the distance from x to 3 on the number line. So, if absolute value of x minus 3 equals 2, that means x is 2 units away from 3. That can happen in two places, 2 units to the left of 3 and 2 units to the right of 3. These distance ideas will guide every equation and inequality we solve in this lesson. Now let us write the core rules. First, for an equation, if the absolute value of x minus a equals b, with b positive, then x equals a minus b or x equals a plus b. Distance b can appear on either side of the center. Second, for a less than inequality, if the absolute value of x minus a is less than b, then x lies inside one interval. Algebraically, that becomes a minus b less than x less than a plus b. Third, for a greater than inequality, if the absolute value of x minus a is greater than b, then x lies in two outside regions. Algebraically, x is less than a minus b or x is greater than a plus b. So you can remember less than means inside one interval, greater than means outside in two intervals. And on the graph, equations will give marked points while inequalities will give shaded regions. Example 1. Solve absolute value of x minus 2 equals 3. First, let us solve it graphically in the coordinate plane. We draw the V-shaped graph of y equals absolute value of x minus 2 with its vertex at x equals 2. Then we draw the horizontal line y equals 3. The solution of the equation are the x coordinates of the intersection points of these two graphs. On the picture, we can see two intersection points, one at negative 1, 3 and one at 5, 3. So, from the graph, the solutions are x equals negative 1 and x equals 5. Now let us confirm this algebraically. Absolute value of x minus 2 equals 3 means the distance from x to 2 is 3 units. So we split it into two equations, x minus 2 equals 3 or x minus 2 equals negative 3. From x minus 2 equals 3, we get x equals 5. From x minus 2 equals negative 3, we get x equals negative 1. So the algebraic method gives the same two solutions as the graph x equals negative 1 and x equals 5. Example 2. Solve absolute value of 2x minus 4 equals absolute value of 2x minus 5. Graphically, we draw two V-shaped graphs on the coordinate plane. Y equals absolute value of 2x minus 4 and y equals absolute value of 2x minus 5. Each is a V-shape with a slightly different center. The solution is the x-coordinate of the point where the two graphs meet. On the graph, we see they intersect at a single point, and its x-coordinate is 9 over 4, so graphically, x equals 9 over 4. Now solve it algebraically. If two absolute values are equal, then one expression can be the negative of the other. We use 2x minus 4 equals negative bracket 2x minus 5 bracket. Now expand the right-hand side. 2x minus 4 equals negative 2x plus 5. Add 2x to both sides. 4x minus 4 equals 5. Add 4. 4x equals 9. Divide by 4. X equals 9 over 4. Once again, the algebraic solution matches the intersection we saw on the graph. Example 3. Solve absolute value of x plus 3 is less than or equal to 2. This time, we will do the graphical solution fully in the plane. We draw the graph y equals absolute value of x plus 3. Then we draw the horizontal line y equals 2. The inequality says we want the point where the v graph is on or below the horizontal line. On the screen, we can see that the two graphs intersect at x equals negative 5 and x equals negative 1. Between these x values, the v graph lies below or exactly on the line y equals 2. So the shaded region in the plane sits between these two intersection points. Reading of the x values, this corresponds to negative 5 less than or equal to x less than or equal to negative 1. Now, algebraically, absolute value of x plus 3 less than or equal to 2 gives the compound inequality negative 2 less than or equal to x plus 3 less than or equal to 2. Subtract 3 from all three parts. We obtain negative 5 less than or equal to x less than or equal to negative 1. So the algebraic interval matches exactly the region we shaded between the two graphs. Example 4. Solve absolute value of 2x minus 8 is less than or equal to 6. Graphical solution in the plane. We draw y equals absolute value of 2 minus 8 and the horizontal line y equals 6. The inequality tells us to keep the parts of the v graph that lie on or below the line y equals 6. We can see on the picture that the graphs intersect at x equals 1 and x equals 7. Between these x values, the v graph stays on or below the horizontal line. So we shade the strip between the two intersection points under the line y equals 6 and above the x-axis region we care about. The corresponding x values are from 1 to 7, including both endpoints. Now solve it algebraically. Absolute value of 2x minus 8 less than or equal to 6 becomes negative 6 less than or equal to 2x minus 8 less than or equal to 6. Add 8 anywhere. 2 less than or equal to 2x less than or equal to 14. Divide by 2, 1 less than or equal to x less than or equal to 7. So the algebraic answer is the same interval we read from the graph. Example 5. Solve absolute value of 2x minus 5 is less than 1. Graphical solution. We draw y equals absolute value of 2x minus 5 and the horizontal line y equals 1. Because the inequality is strict, we want the part of the v graph that lies strictly below the line y equals 1. On the graph, the two curves meet at x equals 2 and x equals 3. Between these x values, the v shape is below the line. So we shade the region of the plane between x equals 2 and x equals 3, and below y equals 1, along the graph. Reading along the x-axis, this gives 2 less than x less than 3. Algebraically, we write negative 1 less than 2x minus 5 less than 1. Add 5 everywhere. 4 less than 2x less than 6. Divide by 2. 2 less than x less than 3. So the algebra confirms the shaded interval from the graph. Example 6. Solve absolute value of x plus 2 is greater than 3. Graphically, we again work in the plane. We draw y equals absolute value of x plus 2 and the horizontal line y equals 3. This time the inequality is greater than. So instead of the middle part, we want the parts of the v graph that lie above the line. Looking at the graph, the two intersection points are at x equals negative 5 and x equals 1. Between these two x values, the v graph is below the line. Outside this middle zone, the v graph lies above the line. So we shade two regions in the plane, one to the left of x equals negative 5 and one to the right of x equals 1. On the x-axis, the solution is x less than negative 5 or x greater than 1. Algebraically, absolute value of x plus 2 greater than 3 gives two inequalities, x plus 2 greater than 3 or x plus 2 less than negative 3. From the first, x is greater than 1. From the second, x is less than negative 5. Again, the algebraic union of intervals matches the two shaded regions on the graph. Example 7. Solve absolute value of x is less than or equal to 9. Graphical solution in the plane. We draw the graph y equals absolute value of x, the standard V shape centered at the origin. Then we draw the horizontal line y equals 3. The inequality asks for the part of the graph where y equals absolute value of x is on or below the line y equals 3. So we highlight the central part of the V graph that sits under this line. The intersection points occur at x equals negative 3 and x equals 3. So we shade the region of the plane corresponding to the x values between negative 3 and 3 under the line y equals 3. Therefore, the x values satisfy -3 less than or equal to x less than or equal to 3. Algebraically, absolute value of x less than or equal to 3 gives -3 less than or equal to x less than or equal to 3. So the algebraic interval is exactly what we saw in the graph. Example 8. Solve the absolute value of x plus 2 equals 4. We draw y equals the absolute value of x plus 2 and the horizontal line at y equals 4. So the solution is the intersection between these two graphs. And we can see that this happens at x equals 2 and x equals -6. Algebraically, absolute value of x plus 2 equals 4 gives two equations, x plus 2 equals 4 or x plus 2 equals -4. From the first, x equals 2, and from the second, x equals -6, so the two solutions match the points we marked on the graph. Example 9. Solve the absolute value of x is greater than or equal to 2. Graphical solution in the plane, we draw y equals absolute value of x and the horizontal line y equals 2. Since the inequality is greater than or equal to, we take the parts of the v graph that lie on or above the line y equals 2. On the graph, the intersection points are at x equals -2 and x equals 2. Between these two x values, the graph lies below the line, and outside this middle region, the graph lies above or on the line. So we shade two outside regions in the plane, one left of x equals -2 and one right of x equals 2. On the x-axis, this means x is less than or equal to -2 or x is greater than or equal to 2. Algebraically, absolute value of x greater than or equal to 2 becomes x greater than or equal to 2 or x less than or equal to -2. So the algebraic description of the solution matches the shaded regions. Now it is your turn. Pause the video and solve these quiz questions. For each inequality, we want you to follow the same method. Draw the graph of the absolute value function and the horizontal line. Shade the region of the plane where the inequality is true. Then read all the corresponding x values and write the algebraic solution. Write your answers in the comment section, and I will review the answers and mention them in the next lesson. Now let us recap. Absolute value means distance. Equations with absolute value usually give marked points on the x-axis, found either from intersections of graphs or from simple algebra. Inequalities with absolute value give regions. You can see them as the parts of the v-graph above or below a horizontal line, and then translate them into intervals or outside regions on the x-axis. In every example, the graphical solution and algebraic solution must agree. Thanks for watching Think Math. For more lessons, visit my website at gamalhamid.net.